Welcome. The title of today's notes is Introduction to the Trigonometric Functions. And today's lesson represents a little shift in the curriculum. We're going to see if we can apply some of the foundational pieces that we've been developing over the last couple weeks. Again, it represents a little bit of a shift here. So let's start it out. We're going to do a little investigation to get the ball rolling and kind of just see where it leads us today. So it says on your paper, the largest Ferris wheel in the world, the Singapore Flyer, is located in Singapore. It is comprised of a 492-foot diameter wheel, and a complete rotation of the wheel takes 37 minutes. Suppose you ride the Ferris wheel for 2 full turns, and that you hop on at t equals 0. Let h of t be your height above the entry point, and t be the time you ride the Ferris wheel. So what we're going to do is look at this as a function, and we're going to have two variable quantities here, and the height above the entry point is going to be dependent on the time. So height as a function of time. And what we're going to do is represent this function in two different ways at this point. One, we're going to represent it as a table, and in two, we're going to represent it as a graph. At some point in time, we'll be able to represent this as an equation, but that's going to take some time to develop. So let's do this. Before we even create the table of values that it says on your paper, let's just draw the Ferris wheel, just get an idea of what's going on here. So I have my circle, of course, and we've been looking a lot at circles over this unit. And it looks like I have a 492-foot diameter, something like this. And we're going to get on right at the entry point right here, and we're going to go around the Ferris wheel, kind of like that. Now, you don't have to do this on your paper if you don't want to. I'm just going to sort of divvy this up a little bit. Just kind of have that x-axis and y-axis in there. Not that it matters a whole lot by any means, but I'm just going to have that in. Maybe it'll help us visually on a couple things. Okay, well, let's start this out here. We're going to fill in some values and see what we would think in terms of these particular t values, what would be the corresponding height values. And you'll see how I divvied this up. So let's kind of start it out right off the bat here. T is in minutes, h of t is in feet. And basically, when you get on the Ferris wheel, you're getting on at the bottom. So your height above the entry point is really 0. So that's going to be one of the points, x and y, or input and output, 0, 0. Now, here, as you can see, this is the 37 minutes right here, everyone. And that's the time it takes for one full rotation. So what I've done with these values, everybody, is sort of divided up into quarters. So this would be a quarter of the way around. This would be halfway around. This would be 3/4 of the way around, and so forth. So if you think about this, and I guess I am glad I kind of did this piece right here, if I get right here after 9 1/4 minutes, that would be a quarter of the way around, what would my height be above the entry point? Well, with a 492-foot diameter, half of that I have as 246. So I'm hoping everyone's in agreement on that piece, that you'd be halfway up the Ferris wheel basically at that point, and that would be 246. Okay, so after 18.5 minutes now, take a look at the Ferris wheel, everybody. You'd be up at the top, and if I'm up at the top, that's 492 feet. Then notice what happens, and again, always sort of relate this to the unit circle, of course, coming back down, and so in this case, after 3/4 of the way around, I'm back at the halfway height, 246, and then after 37 minutes, everybody, back at ground level there, and so it's 0. Excellent. Now what makes the trig functions unique, probably compared to all the other functions that we've looked at in this course, is the next piece. So if you kind of look at this time frame, and this time frame, and this time frame, and this time frame, representing the second time going around the Ferris wheel, what happens to my height values that I had in place on the first round? Well, I hope you would all be in agreement. They repeat. And again, that's what makes the trig functions pretty unique, is that our values repeat forever and ever and ever. They are what are called periodic, as we're going to see. And if I kept going a third time around, a fourth time around, a fifth time around, etc., these values would continue to infinity. Okay, so we're going to kind of stop it right there after 2 rounds. And that would be one representation of a function here. Inputs and outputs, time and height. And now what I'd like to do is actually take a look at this graphically. What would happen if we put those on the coordinate plane what type of graph would it produce? So here's what I'm going to ask you to do, and we're going to focus on this piece right here where it says graph. I notice I only have positive values here, so what I'm going to do, everybody, is kind of make a very elongated L, just kind of the first quadrant there. Something like that should do. And so this will be my origin right down here, everybody, so I'm going to throw a little 0 in play. And then I guess as best as possible here, everybody, we're going to get the height values and the time values going along each axis. Now remember, of course, height depends on time, and so height is going to be on the y-axis, the dependent variable axis, and so just to the best of your ability, kind of throw those pieces in. Doesn't have to be perfect there, but something like that would do. And then this is going to be the trick for me, so I'm going to try to do these evenly spaced as best as possible. So let's see, for me this would be 37 minutes, something like that, and then again 1, 2, 3, and 4, and this will be 74 minutes then as a result. So 37 times 2 there for the 2 times around, and that's looking pretty good. If you want to put some others in, that's fine, but I'm going to leave it like that just for the time being. So this is time, and this is height in terms of time. Time is in, in minutes, and height is in feet. Okay, so what I'm going to ask you to do, maybe you can beat me to the punch here, what I'm going to ask you to do, everybody, is actually plot the points from the table onto this coordinate plane. Now don't play connect the dot, please. That's one thing you're going to have to avoid. Don't connect, just plot the individual points for right now. So I'll do it as well. We said 0, 0 is on there. And in this next one, I'm going to do this. Being at the board, it's a little hard to get a good perspective on this. I'm going to do the best I can. So something like that. I have a shadow in my way, plus I'm kind of looking at the board from an angle. So it's not ideal, but hopefully yours will look better than mine, to be honest. Let's see, so something like this. Okay. There we go. Okay, finally. Okay, now I hope everybody would be in agreement that we do have to play a connect the dot. I don't jump from 0 feet to 246 feet. No, what I do is I cover all of the heights in between. So I do have to actually account for that piece. The question is, how am I going to account for that piece? So it looks like I have a couple questions here to get us thinking in the right direction, and we'll see if we can put this together. So it says, when you connect the points in order to make a continuous graph, and I'm assuming you would agree that it has to be continuous there, as I do cover all the heights from 0 to 492 and back again. The question is it linear? Basically, the question is going to be, am I going to go ahead and just do kind of a V here? Straight, 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 kind of like that. Well, let's think about this for just a second. For something to be linear, the rate of change has to be constant. In this case, as we move around the circle, the height has to be changing at a constant rate. Now let's be clear about this. I am moving around the circle at a constant rate. But the question is my height changing at a constant rate? And if you think about that, well, here I am at the beginning, and as I'm going across, I'm really not covering a lot of height here. It's only when I start to get to, I would call this the 3 o'clock position, then you could see I'm starting to gain height faster. And as I move around a circle, what happens as I get towards the top? Well, I'm not gaining a ton of height. So it looks to me, even though we're moving around the circle at a constant rate, the height is not changing at a constant rate. And so is it linear? Absolutely not. And so what we have to do is account for exactly this piece, that here I'm not gaining height very quickly, here I am gaining height very quickly, here I'm not, etc., and that's changing as we go through. So what is the nature of the graph? And here's just what you're going to write in. It's what's called a smooth wave-shaped curve for right now. That's what you're going to put in place. Smooth wave-shaped curve. What is called a sinusoidal curve, as a matter of fact. Now I'm going to try to do it justice up here. You're probably going to be able to do a better job on your sheet. But I'm going to try to go ahead and now account for exactly how I describe the height. Initially, not changing dramatically. But as I get closer to that 3 o'clock position, it starts to steepen a little bit. And as I reach the top, it starts to level off a little bit, kind of like that. So it's a little tougher for me to come back down this way, but I'm going to see what I can do. Same thing, coming back down. And that would be once around right there. Smooth, wave-shaped curve, a sinusoidal wave. Okay, and then I'm going to repeat the process because obviously I get back down and then I just start it again and theoretically again and again and again, etc., etc. And that is our first look at the trigonometric graphs. Okay, so as I said, basically what we're doing here is representing this function in 2 different ways, once with the table of values and then once with the graph. And now you can see the graph and kind of how it's different from all the others. Now don't put this on your paper, but theoretically this just goes forever and ever and ever and so forth. And again, that's what kind of makes these functions a little unique compared to things we've seen before. All right, just some characteristics you're going to have to be comfortable with today. So let's look at them. 1, 2, 3. Number 1 is what's called the period. Number 2 is what is called the midline. And number 3 is what is called the amplitude. So let's go ahead and read each and throw them into the graph. I'll just be going back and forth on my screens here, and you guys help me out as well. So the period of a trig function is the time it takes for the graph to repeat. And just underline this piece if you don't mind. So it means I need to be in the same position on the graph, going in the same direction. That's key. So let's go back, and I always go from the y-axis. So let's kind of look at this. And you can think about how long does it take for my values to repeat? Well, if you sort of look at this, if I start at my y-intercept right here, I'm going to kind of go from here. How long does it take for me to get back on the graph in the same spot? Oh, it looks like 37 minutes. Here I'm at the bottom, and here I'm at the bottom. So I'm going to try to draw this in as best as possible. So this would be 37, and that's the period. 37 minutes. And what that basically means is I can be anywhere on my graph. I'm just going to pick a spot. You don't have to do this on your paper. Just kind of look at the screen here. I'm going to be anywhere on my graph. 37 minutes later, here we go, 37 minutes later, I'm in the exact same position. So no matter where I am, there is a repeat of that exact same value every 37 minutes. And that makes sense. If you look at the Ferris wheel, of course, let me just come over here, pick a spot on the Ferris wheel. 37 minutes later, I'm back at the same spot, of course. And we show that on the graph, of course, and that's the period. Now, one thing to note, again, same spot, same direction. So notice in this case, I'm here going up. Some people over the years have said, hey, wait a minute, what about this? Can't this be the period just from here to here? No, because here I'm going up, here I'm going down. That's not the period right there. That would be on your Ferris wheel. That would be here and here. That's not the case. Okay. So same spot, same direction. Okay, so period is in play, everybody. That's the first order of business. Let's go ahead and see what we have. What is the period? And the period is definitely, in this case, 37. Our units was minutes here. So the period is 37 minutes. Okay, midline. The midline of a trig function is a horizontal line halfway between the absolute max and the absolute min. So it says what is the midline and label it on the graph. Let's do exactly that. So if you notice, one of the other things that's a little different with these sinusoidal functions compared to some other functions we've seen, it has an absolute max and an absolute min. It has a high point and a low point, and those just keep repeating forever and ever. Halfway in between 0 and 492, everybody, is that 246. So just a dotted line would be fine right there. Now typically you would write this, if you remember, a horizontal line is y equals, or in this case the height equals. You could do y equals 246 if you'd like on your paper, but essentially that would be the midline. As a value, it's going to be more important to us, the 246, not me writing it as an equation. Okay, so we have two pieces in. And again, if you go to the next piece, it says what is the midline. If you want to just write 246, I can live with that. But because it is a line, theoretically it does have an equation. And a horizontal line is y equals. In this case, the height equals. All right, so we have two pieces of the puzzle taken care of. These are the characteristics you're going to really need to account for. So we've got the period, we've got the midline, and the third one, everybody, is what's called the amplitude. The amplitude of a trig function is the distance between the midline and the absolute max, or you can consider it as the midline to the absolute min. And so it says, what is the amplitude of this? So let's, wrong way. There we go. And so amplitude is from midline to the max or midline to the min. And again, it's up to you how you want to pull this off. I'm just going to go ahead and, as a distance here, everybody, that seems to be from 246 up to 492. And so that would be 246 units. I could have theoretically done it same thing down here, going down, 246. So either way works, just easier visually for me to do it that way. And so let's see how we want to write that in. I'll just go ahead and draw that, and that is what's called the amplitude. Okay, so we have now the three characteristics. There will be a fourth one that we're going to investigate in the near future, but for right now, those three look pretty good. So what is the amplitude of h of t? Definitely 246. Now, by the way, it is just coincidence that the amplitude and midline are the same number. It's just because of this particular graph. I can kind of show you why that is if you want to ask independently. But again, that's coincidence, nothing more. Most of the time, they'll be different. Okay. And it just says on your paper, can the amplitude be negative? Let's see. First of all, the amplitude as a distance between the two cannot be negative. So when I ask you for the amplitude of a particular function, you will describe it as a positive number. But let me be very clear about one thing. How we apply the amplitude into our sinusoidal function when we write an equation, you're going to see it go either way, positive or negative. But for right now, amplitude can only be positive. Okay, perfect. Looks like I just have a review problem just to talk a couple things out with this. And then we'll start to round it out here and see how it applies to sine and cosine and see if you're able to make the connection. That's the beautiful piece about this. So I guess before we do that, let's do this just quick review problem here. It says use the formula V equals RW, that's a blast from our past here, to determine the linear speed of a seat on the Ferris wheel. So it is the largest Ferris wheel in the world. I am curious how fast it moves. My understanding is it does move continuously, so I'm assuming pretty darn slow. But let's take a look. So what I saw, first of all, is the radius is going to be 246 feet. So let me get that in there. That's just what I was thinking on this. So radius as 246. And I'm going to want that angular speed, and I think we could pull that out if you remember correctly. The information in the problem, of course, is that there's one revolution in 37 minutes. I think that's the key information. Now think about this. This is a good little test to see if you're on board with me. How do we go from revolutions to radians? We've done this before. 2 pi radians, of course, is the same as 1 revolution. Those are going to cancel out, everybody, and I get 2 pi over 37 radians per minute. Beautiful. So we have a radius, of course, and now I've got a W. Based on the 1 revolution in 37 minutes, I have an angular speed. And then let's just go ahead and put the two together here. V is equal to 246 feet times the 2 pi over 37, and that would be radians per minute. By the way, when we start to write sinusoidal functions, this angular speed actually kind of pops up a good connection in our sinusoidal functions. But for right now, of course, just dealing with it as V equals RW. And let's go ahead and put those together. So I get, when I put this together on mine, and I'm not going to pull up my calculator. If you want to go ahead and do this, that would be great, actually. But take 246 times 2 pi divided by 37. I get 41.77 feet per minute. I happen to think that just miles per hour is a better unit to talk about the speed. So I would ask us to convert to miles per hour, and I won't waste our time with this. I know you can all sort of pull this off. And if you go ahead and multiply by 60 and divide by the 5280 there, you end up getting just under half a mile per hour, just from what I have on my sheet. And so that looks pretty good. again, just a review problem. Sort of fits obviously as a point moving on the Ferris wheel is moving in circular motion. And so as it's changing its distance over time, we can talk about its speed. Okay, good. Let's go get the last piece. So what you're going to basically see is that the behavior of the sine values and the behavior of the cosine values that we have now been developing for at least 2 or 3 weeks, that behavior is identical to the behavior of a point moving around in circular motion. And so what you're going to find is to write an equation to model that graph that we just drew about 5 minutes ago, it requires either a sine or a cosine function. They are essentially interchangeable. We're going to talk about pros and cons for each as we go through our process. But at this point in time, you should understand really not just some of the special values, which I have in the table right here, but more importantly, the behavior of these values as a point moves continuously or as an angle changes in radians continuously. And so let's fill it in. I think you know some of these. Well, should know all of them. So sine of 0, everybody, is 0. So what we're going to do is now treat this as a function. This is the independent variable. This is the dependent variable. Essentially what this represents, everybody, is the angle measure in radians. And remember, an angle in radians is just a real number. So I can take the sine of any real number. When I do that, the output essentially is the ratio, the sine ratio, how we defined it. And remember how we defined it, really the vertical part over the direct part. We called it the y over r, but really it's the vertical over the direct, that ratio. So independent variable is the number, dependent variable is the ratio. Okay, well what is the sine ratio at pi over 6? 1/2. Sine ratio at pi over 4, 0.707. Now again, you know this is root 2 over 2. You know this is root 3 over 2. You know this obviously, well, it's just 1. Sine of pi over 2 is 1. Now what happens to the sine values after I hit pi over 2? They start to come back down, as we all know. Again, really should understand the behavior of these values at this point in time. And by the time we hit pi, halfway around our unit circle, the sine of pi is 0. And again, you should be able to see that. That's the beauty of it. It's not just memorization. It's the visualization piece. And as I keep going, then we start getting into the negatives. So negative 0.5, negative 0.707, negative 0.866. What happens when I get to the bottom of the unit circle? The sine ratio is negative 1. Can I ever have a sine ratio below negative 1? Nope, because those numbers now start to come back up. And you can really see them unfold. And by the time I hit 2 pi, or once around my unit circle, I'm back to 0. Now what would happen if I went again around my unit circle? If I continued this table, what would happen to all these values, of course? They would repeat, just like we saw in the investigation with the Ferris wheel. Okay, so guys, what we're going to do here is create what is called a z-trig coordinate plane. We're going to see this on the calculator in just a couple minutes. So here's how I'm going to have you do it on your paper if you're ready. I'm frozen here for a sec. There we go. So give me a fairly elongated coordinate plane horizontally, kind of like that if you would. And I guess for our purposes here, let's just go ahead and put a 1 up there and kind of match it with a negative 1 down there. And then what we're going to do, just try to evenly space them if possible. 4 tick marks, everybody. And this is going to represent pi over 2, pi, 3 pi over 2, and 2 pi. Okay, so please get those 4 tick marks taken care of. Again, those are what are called the quadrantal angles, separating the 4 quadrants. And what we're going to do is plot a few of these points just to get a sense of it. And we'll go back in just a couple minutes here, but let's get this first rotation taken care of. So bear with me on this piece, and you can do this or not do it. It's your call. But essentially, the sine of 0 is 0. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is negative 1. And the sine of 2 pi, everybody, is back to 0. Now again, I would ask the question here, as I go ahead and connect the dots, do I want to do it in a linear fashion? No, of course not. what I want to do is that nice, smooth sinusoidal wave. That's how the behavior of the sine values are. And so we're kind of at the middle here, so this kind of comes up right away. Something like this. Give or take should look something like that right there. Okay, now again, if I went on and on counterclockwise, would this go forever and ever? Oops, made a little mark there. Would that continue? Sure it would. If I went clockwise around my unit circle, could I kind of figure out the same results? Well, of course. So the other part to the z trig coordinate plane would be going clockwise. Negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. And basically what you're going to do is take this one rotation right here, and you're going to copy it or paste it over to this rotation right here. Because if I went clockwise, well, the sine of negative pi over 2 is negative 1. That's down at the bottom of the unit circle. Sine of negative pi is 0. Sine of negative 3 pi over 2 is actually at the top of the unit circle, et cetera, et cetera. So you end up getting, when all is said and done, something like that. Now, what I would encourage you to do, it's kind of silly to do, but just to emphasize, put a little dot, dot, dot right there, and how about a little dot, dot, dot right there? Does this go forever and ever in both directions? You bet. It sure does. Wonderful. Hey, everyone, let's bring up the calculator for just a sec. And what you're going to have to do is this branch of trigonometry is really this modeling that we're going to be doing now for a little bit here. It's all in that branch of the trigonometry of real numbers. And so anytime we're in the trigonometry of real numbers, what we're doing is taking the sine and soon to be cosine of just an ordinary number. Well, that's radian mode. So please make sure you're in radian mode on the calculator. And then just go to your y equals and type in sine of x. And when you get an opportunity, after you've typed in sine of x, hit the zoom button at the top. And you'll notice, of course, right below the standard window is the z-trig window. And so you can just hit number 7 there if you get an opportunity. And then there it is, of course. Does that graph look like mine? Well, sort of. That one's better. But you definitely get an idea of it. And notice, everyone, the sine function starts at the midline, goes up, comes down, ends at the midline. Keep that in mind if you would. All right, everyone. Let's go ahead and just take a look at the cosine graph, and then we'll wrap this on up momentarily. Okay, here we go. So, same deal, everyone. Box this up if you would. Taking a look at the cosine function for the first time. We can take the cosine of any number in existence. So this is just going to be any real number. When I do that, I'm going to get a particular ratio. This represents the ratio. That ratio, if you remember correctly, we defined it a couple different ways, but ultimately it is the horizontal distance over the direct distance to a particular point. And so it's x over r is the way we described it, but it's really the horizontal over the direct. And those ratios have only particular values, and that's what we'll see in this table. So let's go see. Cosine of 0, by the way, is 1. Cosine of 0 is 1. Cosine of pi over 6. Oops, I wanted to write root 3 over 2 there. Let me do it as the decimal, 0.866, 0.707, 0.5. And cosine of pi over 2 is definitely 0. Now what happens in the second quadrant, everybody? They become negative. And so let's see, negative 0.707, negative 0.866. What happens when I hit pi, everybody? Cosine of pi is negative 1. Excellent. And it continues in the third quadrant. You're probably going to be able to do this quicker than I can do it, but basically that's what happens right there. Again, the behavior of those cosine values. And in the last quadrant here, 0.5, 0.707, 0.866. What happens when I hit 2 pi? Of course, we come back to 1. Will I ever have a cosine ratio above 1? No. Will I ever have a cosine ratio below negative 1? No, of course not. Same premise, everyone. And as I said before, the sine and cosine are basically interchangeable. We'll kind of look at that in just a little bit on the next lesson. But essentially, let's just get a feel for it. This popped up. Let's get rid of that. So 1 up there, -1 down there. 4 tick marks, everybody. And until you get really comfortable with it, especially on this side, but I would do it on both, until you really know these values here, let's write them in. Okay, again, if you want, you could also put a 1 and a -1 there if you'd like. And then -pi/2, -pi, -3pi/2, and last but not least, -2pi. All right, we're ready. And so what would happen if I kind of looked at some of these values? Cosine of 0 is 1. Come on. So cosine of 0 is 1 at the top. Cosine of pi/2 is 0. Cosine of pi is -1. Cosine of 3pi/2 is 0. And cosine of 2pi is back at 1. And remember how sort of the behavior here. Let's go ahead and get this in, kind of like this. Give or take. Not a great one. And then it just repeats again and again and again. Something like that. Again, how about a little dot, dot, dot right there, a little dot, dot, dot right there. Let's graph this on the calculator just to verify, but get comfortable with seeing this piece. Sine versus cosine. If I gave you one as opposed to the other, you should be able to tell me which is which. So let's go to the y equals there, and you could just peek up on your screen. But I'm just going to do cosine of x and hit graph because I'm already on that window. And you can see, of course, the exact graph that I drew. Just this one looks quite a bit better. All right, wonderful. And that's how it's going to play out. So just to talk really, really quickly about the differences between sine and cosine in terms of their graphs, remember sine started at the midline and came up. Cosine starts at the max and goes down. But it's that same sinusoidal wave for sine and cosine. And so in this case, cosine starts at the max. Sine, everybody, started right in the middle. So it started at the midline, went up, then went down, and back. So just, again, keep that in mind as we'll talk about that process. All right, let's get rid of that calculator up here. And just try a couple things out with this particular unit. Just get comfortable with the idea behind a sinusoidal wave, and that we're going to be modeling those types of graphs with either the sine function or the cosine function. Excellent. Well, thank you for listening, of course. If you have questions, just let me know.